All right, this is Unit 3, Lesson 3 of our calculus class. Unit 3 is all on implicit differentiation, inverse derivatives, and just a few more extra derivative things we just need to clean up. Lesson 3 is on implicit differentiation at a point. So what we're going to do in this is just more practice with implicit differentiation and look at ways to find the derivative of at a point using implicit differentiation. All right, so some notation on this. We have our dy dx derivative notation, our Leibniz notation. So when we say the derivative at a single point, then we'll put the dy dx, this very vertical bar, and then at a point some value x, y. So x, y would each be some number. So, or we'll just say the derivative at x, y. Okay, now that you've seen the notation, here's an example. So here's our equation. We wouldn't be able to solve this for y as still be a function that we can derive, so we'll use implicit differentiation. And the point we want to derive this at is the point 2, 3. And so at that point, what is the slope of the tangent line for this function? So we'll take first steps, we'll derive this thing implicitly. So dy dx of the left side is equal to dy dx of the right side. Normally I would put this whole thing in parentheses just to be super clear that we are in fact deriving the entire polynomial, not just the term. I didn't do that here, so shame on me. So anyways, if we derive this thing, the constant term washes. The derivative of negative y squared would be negative 2y times dy dx. And then we're adding the derivative of 3x squared, so it would be 6x. And then, of course, the derivative of 0 is just 0. So the second step we're going to do here is solve for the dy dx. So I'm going to subtract 6x over to the right side and then divide both sides of the equation by the negative 2y. So I get dy dx equals negative 6x divided by negative 2y, which simplifies to 3x over y. And so now here's our taking the derivative at this point. So now what we're going to do is say dy dx at the point 2, 3 is equal to our derivative, except we're going to plug in 2 for x, we're going to plug in 3 for y, and that's going to be 3 times 2 divided by 3, which of course is just 2. So 2 is the slope of our tangent line at this point. Okay, we can graph that. So if I have my graph of the function, here it is, it's a hyperbolic. The point 2, 3 is right here, and the tangent line is this orange dashed line right there. So we could see graphically that looks like we did this correctly. Okay, so takeaway here, we can use implicit differentiation, building more confidence with it. We now know what it looks like notation-wise to take the derivative at a point, and we know how to do it.